Okay, so it's been a long time. There are reasons for that I'll go into later, but I know I said that the enclosure video was next, but this is actually going to be a short departure from the bit-based series, and I'll get into the reasons for that in a second. So the specific goals of this episode are going to take the classic Atari Punk console design that sounds and plays like this, and then we're going to take that and have it MIDI controlled instead using SPI controlled digital potentiometers, and that's going to sound and play like this. Now you're probably thinking, why did he decide to do this random video? And there are reasons for that I'm going to get into right now. The first reason is that I've been preparing for job interviews the last couple of weeks and have been going on them as well. And I really wanted to do something that was just fun and back to synthesizer design, not board fabrication, enclosure design, stuff that are kind of out of the realm of synth design, I suppose. And now the other reason for it is that while bit-based, the board fabrication is done and it's a nice tight little circuit, well, I'm also creating a 3D printed design for that, which I actually have already done and printed. And it is also very nicely designed, but it requires a 3D printer. And so one of the reasons that I'm doing this project here is because I'm going to put the board together on perf board, which is you're not gonna have to go through that big fabrication procedure, but it's a little bit jankier, a little bit hackier. And then, but to go with that, we're going to make a very hacky DIY style enclosure where maybe we just drill some holes and some stuff and then mount some potentiometers like that. So basically it's another way to do enclosure design that might be better if you're not looking to get into 3D printing. So I wanted to explore that as well, and this is going to give us a project that we can actually give an enclosure to that's in that style. So since the intention of this episode is to just kind of be a short, fun departure, I'm not going to go in as much detail as I would have gone in the bit-based series. So I got the idea for this episode when I was going through my miscellaneous IC cabinet from my drawer over there, and I found these little ICs here, which are digital potentiometers. Now there is an issue with this and throwing it in an Atari Punk console, and that's that these are 5K digital potentiometers and not whatever value that they use in the original Atari Punk console design. So we're actually going to have to go in and modify the original design to fit our 5K potentiometers. So now let's look at an implementation of the Atari Punk console and then also the 555 datasheet, and we'll see if we can fit that to our the 5K potentiometers to our design. Alright, so here we have the basic Atari Punk console design, and essentially the first 555 here is acting in the Astable multi-vibrator mode, which basically produces a square wave oscillation. And the square wave oscillation is then being sent from the output to the trigger of this next 555 here, which is set up in the Monostable configuration, which essentially allows it to become a frequency divider. Now, every part of my soul is telling me to simulate the circuit for you guys and show you exactly how it works, because I know everything I just said there probably doesn't really make much sense. But unfortunately that would make this episode too long, so I'm going to give you the bullet points instead, and hopefully that's going to help your guys' understanding. So you heard me say Astable and Monostable, so let's jump into the datasheet and see what I mean by that. So like I said, the first 555 is set up in an Astable configuration, and this is going to talk a little bit about the Astable operation here. So like I said, in Astable operation, it's basically just a square wave oscillator. So how? Well, let's talk about that by going step by step. So let's assume here that the trigger, which is this pin here, is starting low, which brings the output high and then allows this capacitor here to charge. And when it gets to 2/3 the supply voltage, the output goes low and the discharge pin is allowed to sink current, which means that the capacitor then discharges through pin 7 here, which is the discharge pin. Since the trigger is connected here as well, then the trigger gets pulled low and then this whole process starts again. And that's basically how it becomes a square wave generator. So you'll notice here it's got this resistor here, RA, and then RB, and then this capacitor here. If we jump to the Atari Punk console, you'll see that it is the exact same layout here with the capacitor over here. There's also a couple other differences here. One of the things is that we have this other capacitor here from pin 5 to ground. That's just a stability thing. Don't worry about that for our purposes here. Also, these resistors here, which are essentially the loads, don't worry about that. So now you should understand that we have a square wave oscillation coming here out of the output. Now this next one right here, this next 555, is in monostable mode, and thankfully that's a little bit easier to understand here. So let's go up to the datasheet here, and once again let's go step by step. So let's assume the trigger is low at startup. Then the output goes high, and next this capacitor here starts to charge. When it reaches 2/3 of the supply voltage, the output goes low and the discharge pin is allowed to sink current, which brings the capacitor back down to 0 volts. And the output remains low until the trigger receives another low pulse. So essentially it creates a pulse every time a low pulse is sent to the trigger, with the length of the pulse being determined by this resistor here, because of course that controls the charge time of this capacitor here. And with this configuration we just have this resistor here and then this capacitor here. And if we jump back to our Atari Punk console, we see that we get the exact same configuration here. So to understand why the Atari Punk console really gets that stepping sound that it's known for, let's kind of go through this step by step, looking at the whole circuit diagram. So we know that we have our first Astable 555 configuration generating a square wave oscillation at a frequency determined by these resistors here. The square wave is then sent to the trigger pin of our next 555 configuration, which is a monostable configuration. Now, depending on this resistor here, we may be receiving more than one low pulse per the capacitor charge rate. So really think about it. If we were receiving multiple low pulses before the threshold here gets to 2/3 the supply voltage, we're really only outputting one single high voltage in that time period. So let's say that during the capacitor charge time, one additional low pulse is sent to the trigger pin but ignored. Then what happens is we've just divided the voltage by 2, and that's our output. So essentially, we're just using this second one here, like I said, as a frequency divider. So that should give you an understanding as to why controlling this resistor here gives us that stepping, because it's a different amount of division going on. So hopefully you guys have a pretty good understanding of how that works, but now we really need to modify it. So thankfully, they've included formulas here for us to calculate the period of the capacitor charge for the monostable configuration, and then also the frequency of oscillation for the Astable operation. So let's figure out how we can supplant this with our 5000 ohm resistors instead of these 470 kiloohms. Okay, so to get our digital potentiometers into this design, we're basically going to have to change the design to fit to be as close as possible to the original frequency ranges. So we are going to get into a little bit of math here, but it's like high school algebra, nothing you should be afraid of. So from the datasheet, we got that this equation here is how we're going to calculate the frequency. And we also know that in the Atari Punk console design, RA here, this resistor is a potentiometer that is a 470 kiloohm potentiometer. So it can range from 470 kiloohms to 0 ohms. So once we calculate all this down, we basically get a frequency range of 305 hertz to 72 kilohertz. So that's going to be our target frequency range. So now the next step is going to be basically solving for the values here. What we know now, for example, that since we're using our digital potentiometer, this number here, instead of being 47K as a potentiometer, we're going to use 5K as the potentiometer. So now the question is, what do we need for RB, which is the second resistor, and then what do we need for our capacitor? Well, since we are going to be we're going to be using lower resistances, that means that we're going to need a bigger capacitor. So I'm going to go ahead and I'm going to give this a 1 microfarad capacitor, which that's what it ends up being. So now we need to solve for X here, and we're going to try and get as close as possible to this frequency range. Now, I'm not gonna go ahead and do that math because it would be boring and stupid, but basically what this X ends up being is 10 ohms. So now what we have is we have RA equal to 5,000 ohms, bad handwriting. RB, bad handwriting, equals 10 ohms, and then our capacitor is 1 microfarad. Also, these new values, basically they're gonna change the frequency range, but only right here, and they're actually just gonna widen it up a bit to 287 hertz. So we get a little bit lower frequency as well, but that's still in the audio range, that's still great. All right, so now that we have our Astable components figured out, the next step is to figure out our Monostable components, which we can do with another equation from the data sheet. And this is basically going to give us our capacitor charge time. So with the components that we have now from the original design, which is a 470K ohm potentiometer and then a 0.1 microfarad capacitor, we get from 0 seconds to 0.0517 seconds. So now to get as close as we can to this range, we're gonna use the same exact high school algebra techniques. So we're gonna remove this and replace it with the 5K that we know is going to be in the digital potentiometer, and then solve for X, which is this here. And I'm not gonna show the math again because it's just simple, but basically the closest usable capacitor value that we end up with is 10 microfarads. And what that gives us is a pretty close range of 0 to 0.055 seconds. Bad handwriting. So I'm pretty happy with those ranges. So let's actually put it on the breadboard and see what it sounds like. So pretty cool. It still sounds like a traditional Atari Punk console. So one part that's a little bit bad about Atari Punk consoles, in my opinion, is just how unintuitive it is to play with them using potentiometers. So let's get into the fun part, which is actually adding the digital potentiometers and get some sequencing going. So the digital potentiometers that we're using are going to use SPI or SPI as the communication protocol, but other than that, they're the exact same as regular potentiometers. So they have the 3 pins. They have the wiper, and then they have the first pin and the second pin, or the last pin, the third pin. So here is the final Atari Punk console schematic that I've got going on here. And you're gonna see that aside from the Arduino and some of the UART stuff going on, and then some switches, we have at its core, the exact same Atari Punk console design as the original that we looked at before. So if you've been working along with BitBase, you're gonna know that SPI and UART for the MIDI control is something that you've already worked on. And actually what we're gonna end up doing is we're gonna recycle a lot of the code from BitBase and use it in this project. So let's jump into the code and see exactly how we're controlling this thing. All right, so the first thing that we're gonna do is generate our MIDI and peripheral setup files. For our peripheral setup, we need to set up our USART for our MIDI input and output. So we'll copy and paste the code from BitBase since it will be the exact same. For our SPI, we're gonna need to modify the code a slight amount. So let's start by copying the SPI DAC master init function. This function will be the exact same, except now we have 2 chip select pins. So in addition to pin B2, we need to set pin B1 as an output in DDR-B. We'll also set pin B1 high since we're not writing to the potentiometer immediately. And finally, let's change the function name to SPI pot master init. Now for actually transmitting our data, it's actually gonna be easier if we just write a new function because it's kind of different. So if we were to take a look at the data sheet, which I'm not gonna do here for the time purposes, but if we did, we would find that we need to send 2 bytes of data to the potentiometer. And the first is essentially a configuration byte. And the pot has other functions, but we're really just concerned with writing to it. So this byte is nothing but zeros. Now we'll just put that into our register and make sure it's sent with the spin lock. And the next byte contains our data, so sending that is as easy as this. And then finally, we're gonna pull our chip select pin high since our data has been transferred. So this could be optimized a bit more, but this is the basic idea of it, so I'm just gonna leave it. Our MIDI.h file is going to be the exact same as bit bases. So let's just copy and paste that in. And now we're finally ready to implement our MIDI control. So we'll start by including the files that we just wrote. Then we'll prototype our process MIDI event function. In our setup code, we need to start by disabling global interrupts, then calling our initialization functions, and then renabling our interrupts. In our main loop, we're really only processing items in our MIDI event buffer, just like in BitBase, so we'll just do this. Now we'll implement our process MIDI event function. I'm shooting for a quick and dirty implementation that I can send MIDI loops to, so here's how I'm implementing that. First, we check if we have a MIDI note off event. If we do, then we check our note value to see if it's the bottom half of the keyboard or the top half of the keyboard. Basically, I'm making the bottom half control the Astable or oscillator frequency potentiometer, and I'm having the top half of the keyboard control the Monostable or frequency divider potentiometer. And we'll do that like this. Now, if we have a MIDI note off event, I want the sound to go silent, which is why I'm sending this constant value to the digipod. Next, we'll handle the case of a MIDI note on event. For this, we really only need to know if the note is in the top or bottom half of the keyboard and to determine which of the digipods to send it to, and then we'll take that data multiplied by 2 to get the full 8-bit range. Or I'm sorry, multiplied by 4. So you'll also notice that for the second one here, we have to subtract 64 too, because we really want to start that index at 0, not at 64. So let's compile it, make sure it works, and we got a spelling error. All right, so it looks like it compiled well, and that's it. That's all the code for this project. And that said, this is a really quick and dirty implementation. There's so much more that you could do with it, including sequencing through the Arduino, velocity sensitivity, MIDI timing signals being used, and all kinds of other cool ideas. But like I said, this is a quick project just for me, so let's go ahead and just wrap this video up. All right, now we have our MIDI controlled version. Let's make some loops with it. All right, so basically the way that I have this working here is that the top half of the keyboard here controls the frequency divider part, and then the bottom half of the keyboard here is controlling the Astable part, or the oscillations. So let's see how this sounds. So that sounds pretty cool, right? It still has that Atari Punk console sound, and then also you noticed I was kind of playing with the wires there. So what I'm going to do is I'm going to have switches that basically switch between using the potentiometers versus using the SPI controlled digital potentiometers. So you're going to have options there as well. The use case that I'm thinking for this thing is basically I'm going to have some type of MIDI sequencing device that's going to be sending loops to this. And while I could have built a sequencer inside of it, that's kind of the end goal that I'm going for, is kind of to have a master MIDI device that's going to be sending MIDI data to all these different devices while I play other instruments. I've tried to leave the code as open as possible to whatever your use case might be, but I'm going to get more on what I plan on doing with all these devices in future videos after the BitBase series. But yeah, I just want you to open your mind to digital potentiometers and think about all the designs that you've ever worked with before, any little designs that you might have built that used potentiometers. Well, think about it. Could you replace those potentiometers with digital potentiometers and use SPI control or MIDI control or whatever you want to control that instead? Anyways, I'm starting to ramble now. The real point here is that we now have another synth that we can use in the enclosure video, and this is going to be, like I said, a hackier design that we just drill some holes, you know, put in some potentiometers, whatever else we need, and just mount that in firmly in a real hacky way. So yeah, the next video is going to be all about enclosure design, and the schedule for that is basically going to be, first, I'm going to show you how I proto-boarded this design here. Then we're going to go in and build that hacky enclosure design for this synth. Then we're going to go and do some CAD design for BitBase and for the 3D printed enclosure on that, and then I'll show you how I 3D printed it. I really hope you guys enjoyed this departure. If not, please let me know in the comments. If you did like it, maybe also let me know in the comments, I don't know. But yeah, I'll see you guys next time.